Let's have a short lecture to wrap up some ideas about magnetic forces. In particular, what would be the motion of a charged particle in a magnetic field? We know that the force does not increase or decrease the speed of the particle, but it does change its direction. For instance, if you were to look at this diagram here, look at the charged particle on the bottom here. As this charged particle comes in to the magnetic field being into the page, particle going to the right, then we'll have a force on it as going up. So this particle is going to be starting to curve and be deflected in an upward direction. Sometime later, it's actually moving in that upward direction now, and with the velocity going up, field is still into the page, and now the force is to the left. So it's got a force field on the left, it starts curving in that direction. Sometimes later, it finds itself over here. The force is always going to be perpendicular to the direction it's going and inward on this circle. So this particle comes in and starts moving around in a circle where the magnetic force acts as the centripetal force for that motion. So we have that QVB is equal to the centripetal force, mass times centripetal acceleration, v squared over r. Let's get rid of a v on both sides and solve this for the radius of that circle. And we have that it's equal to the mass times velocity divided by the charge times the field. The momentum over the charge times the field. That will be the radius of a charged particle in a uniform magnetic field. If the charged particle were to hit that magnetic field at an angle, then the component of the particle's velocity that actually is in the same direction as the field will go undeterred, undeflected, and the component that's perpendicular will cause a circular motion. So we'll have a velocity that is retained along the field lines and then a circular motion going around the field lines. So the particle will start moving in a helix around those magnetic field lines. This is really what happens when charged particles from the sun impact the Earth. The Earth has a magnetic field going from geographic south to geographic north. And so when charged particles from the sun hit the Earth's magnetic field, they start moving around in circles, and then they are forced to converge at the Earth's poles. When they converge at the geographic North Pole, well, as these particles get closer together, they start losing energy as they collide with each other, and hence a lot of the energy that they have magnetically gets lost in other forms of energy, one form being visible light. So when these particles converge at the Earth's North Pole or the Earth's South Pole, you have a display of light, the aurora borealis at the north or aurora australis at the south, otherwise known as the northern or southern lights. Let's try an example. A proton moving in a circular orbit of radius 14 centimeters in a uniform magnetic field of magnitude 0.35 Tesla directed perpendicular to the velocity of the proton. Find the orbital speed of the proton. Well, let's rearrange this equation and find the velocity. It's going to equal QBr over m. Charge of the proton 1.6 times 10 minus 19 coulombs. The magnetic field was 0.35 Tesla, and we're told the radius of this circle was 0.14 meters. Mass of the proton is 1.67 times 10 minus 27 kilograms. So it's moving at a pretty good clip, 4.7 times 10 to the 6 meters per second. If an electron moves perpendicular to the same magnetic field with this particular speed, what would be the radius of its circular orbit? Well, r equals mv over qb, moving with the same speed as this proton, but with the mass of an electron, 9.11 times 10 minus 31 kilograms, has the same magnitude charge, by the way. It would only move in a circle of radius 7.6 times 10 to the minus 15, or minus 5 meters. So it would be a small fraction of a millimeter, whereas the proton is moving in a good 14 centimeter radius orbit. So you could easily distinguish between the two particles based on the size of their circular motion. The angular frequency of a rotating charged particle is equal to the linear velocity divided by the radius, v divided by r. If we take the previous expression for velocity, we end up with an angular frequency equal to qb over m, or in other words, the charge to mass ratio of the particle times the magnetic field. Note how this angular frequency is independent of the velocity or the radius of the orbit itself. It's only equal to the charge to mass ratio of the particle times the magnetic field. And this would also be true, this independence of the radius and the velocity would be true for the period of the motion. This is what we call the cyclotron frequency and the cyclotron period, respectively. Consider this situation. We have two fields going on. We have an electric field devised by two plates, a positive plate and a negative plate, going vertically. And then we have a magnetic field going horizontally into the page. And we're going to apply this on the same charge. Now the electric field, if it were a positive charge, would force the charge in a downward direction, while the magnetic field, with the charge moving to the right and into the page, would force it in an upward direction. So if I had a slit at the end of this tube, if one force were greater than the other force, then the particle will deflect one way or the other and never make it through the slit. But if the forces just happen to be exactly equal, then the particle will go along that middle line and make it directly through that slit. So the particles that actually make it through the slit are only those particles where the electric force is exactly equal to the magnetic force. In other words, QVB would equal QE. If we get rid of the charge on both sides of this equation, we would find that the velocity of the particles that finally escape through the slit of this velocity selector is going to be equal to the E field divided by the B field, the magnetic field. In other words, if I tweak the electric field and the magnetic field, I can tweak what velocity of particles I want coming out of this device. Cool. That's good, because if I were to have this device and as a precursor to a mass spectrometer, then I would be able to control the velocity of the particles that I'm throwing in to this mass spectrometer. Consider this. Two isotopes of hydrogen, hydrogen and deuterium. Deuterium is one proton plus an extra neutron, so it's about twice the mass of the hydrogen atom. Enter the slit with the velocity, the same velocity of 10 to the 6 meters per second. So they both have gone through a velocity selector. Hydrogen mass is 1.68 times 10 to the minus 27 kilograms. Deuterium is 3.36 times 10 to the minus 27 kilograms. So about 2-to-1 ratio. Find the distance of separation when they strike a photographic plate. The magnetic field is 0.1 Tesla. Well, they're each going to go through a different radius orbit, and that radius is going to be proportional to their mass. They each have the same velocity, they each have the same charge, and they're in the same magnetic field. So strictly speaking, we're going to have a radius of the orbit that separates them in terms of their mass. For the hydrogen, the radius of that orbit is going to be 0.11 meters. For the deuterium, with twice the mass, approximately twice the radius, 0.21 meters, a little bit less than mass, 0.21 meters. So the difference between these half circles would be a distance of 0.2 meters, or about 2 decimeters, that far right there. So if you had two collectors, you could easily separate the isotopes of this element, hydrogen and deuterium, and you'd be able to separate them from each other. You could use this technique on other isotopes of other elements, such as, say, uranium-235 from uranium-238, and hence enrich the uranium to where it could be weapons grade or bomb grade. This is technology that you would need if you wish to make a nuclear plant or a nuclear bomb. And it's a technology that hopefully most third world countries do not have. Here's a deflection in a cathode ray tube, an old style TV set. You can use a magnetic field to deflect charged particles, electron beam in this case, through a vacuum. And as they encounter a phosphor on the screen, either red, green, or blue, and depending on how many particles hit would vary the intensity, you can recreate a color picture on that screen. And that's basically the way that the old style color TV sets worked. A current carrying conductor is placed in a magnetic field in a Hall effect. The charge carriers are displaced to one side of the conductor, leaving the other side oppositely charged from that of the charge carriers themselves. A voltage and electric field would then be established between the displaced net charge. At some voltage, which we call the Hall voltage, the E field force will equal the magnetic force, and then no further charge would be displaced. One consequence of the Hall effect is that the sign of the Hall voltage will determine the nature of the charge carriers, whether they actually are positive or negative. Here's how it might work. We have a conductor material. We have a current flowing, say, to the right. If the carriers were negative, they'd actually be moving in the opposite direction from what we indicate as the current. I have a B field going into the page as you're looking at it. And if we did our cross product, QV cross B, as you're looking at it, it's going to the left into the page. So V cross B would be down, but then the charge is actually a negative charge. So the magnetic force would actually be up, thereby collecting negative charge to the top and positive charge to the bottom, which would set up an E field in the opposite direction, causing the electric force in the opposite direction. At some point, there'll be enough charge buildup so that these forces are equal and no more deflection would occur. Then if you came in with a voltmeter, you can measure the polarity of the potential difference and then determine if that potential difference were negative as we're looking at top to bottom, then we would say, oh, the carriers are negative. We have electrons are our carriers in this material. Likewise, if you did the same thing and positive charge were to develop on top and negative charge on the bottom due to magnetic deflection and then electric field and finally the forces canceling, if you measured that voltage and it came out positive, you would determine that the true carriers in that material were actually positive charge carriers. So the Hall effect is one way to definitely determine what the charge carriers actually are. In metals, it is determined that the charge carriers are indeed electrons. Note that when the electric force balances the magnetic force, we have Q drift velocity magnetic field equals Q electric field Hall effect. The Q's cancel out, so the drift velocity times the magnetic field is equal to the electric field. But we know that the Hall voltage is equal to the electric field times the distance d, where d is the width of the conductor. So we could measure that voltage, and that voltage would be equal to the drift velocity of the carriers times the magnetic field times the distance d for the width of the conductor. Well, we know what magnetic field we're applying, and we know the distance d of the conductor. We can measure that easily. So by measuring the Hall voltage, at least the magnitude of that voltage, we can determine what is the drift speed for the carriers in that material. And that's a very good thing to know. And it's an intrinsic property of that material to be able to ascertain the drift speed of the charge carriers and the sign of the charge carriers. So that is what the Hall effect is good for, determining the drift speed characteristics of a material and the sign of the charge carriers. That concludes the short lecture on magnetic fields and magnetic forces in chapter 29. We will then go on into more in dealing with the Biot-Savart law in chapter 30 and Ampere's law.